the field of quantum computing emerged in the 1980s. It was found that certain computational problems could be tackled more efficiently with quantum algorithms than with their classical counterparts. Quantum computing has the capability to sift through huge numbers of possibilities and extract potential solutions to complex problems and challenges. Quantum computers use qubits, whereas conventional computers store data as bits with either zeros or ones. Qubits carry information in a quantum state that engage 0 and 1 in a multidimensional way. Quantum theory principles which describe how matter and energy behave at the atomic and subatomic level is used in quantum computing. Quantum bits, or qubits, allow these particles to exist in more than one state, 1 and 0, at the same time. Theoretically, linked qubits can accelerate calculations that may take thousands of years by taking advantage of interference between their wave-like quantum states. Several of the most prominent firms, including IBM, Microsoft, Google, D-Wave Systems, Alibaba, Nokia, Intel, HP etc. have taken notice of this massive computing potential. Before proceeding in this video, please subscribe to the channel and share and like the video. Quantum computers have a simpler architecture than conventional computers and they have no memory or processor. The equipment consists solely of a set of qubits that makes it run where trapped isolated ions are the qubits. The quantum computer has three primary parts: an area that houses the qubits, a method for transferring signals to the qubits, a classical computer to run a program and send instructions. With some qubit storage techniques, the unit housing the qubits is maintained at a temperature at absolute zero to increase their coherence and reduce interference. Other types of qubit housing use a vacuum chamber to reduce vibrations and stabilize the qubits. Signals can be sent to the qubits using a variety of methods, including microwaves, laser, and voltage. Many applications could benefit substantially from quantum computing, like security, finance, military affairs, intelligence, medical industry, aircrafts and aviation, nuclear fusion utilities, machine learning, and artificial intelligence, besides information exchange and cryptography. It is also anticipated to aid in environmental difficulties and water quality applications. Quantum computing is based on quantum physics features like superposition and entanglement. They empower quantum computers to handle operations at speeds exponentially higher than conventional computers and with much less energy consumption. The first feature is superposition. The difference between binary position and superposition can be pictured by imagining the coin flipping. Classical bits are measured by flipping the coin and getting heads or tails. However, if you were able to look at a coin and see both heads and tails at the same time, as well as every state in between, the coin would be in superposition. Another way to understand superposition is using the Schrödinger cat example. If you seal a cat in a box with something that can eventually kill it, you won't know if the cat is dead or alive until you open the box. So, until you open the box and observe the cat is dead and alive at the same time. This example can be used to understand the wave-particle duality of the electron observed in the double-slit experiment, where the electron changes its behavior when observed. A qubit places the quantum information that it contains into a state of superposition. This refers to a combination of all possible configurations of the qubits. Groups of qubits in superposition can create complex, multidimensional computational spaces. The second feature is called entanglement, which is integral to quantum computing power. If a pair of qubits are entangled, the two qubits then exist in a single state where changing one qubit directly affects the other in a predictable manner. The main characteristic of quantum computers is that it permits the coherent superposition of ones and zeros. Quantum computing still have some difficulties and limitations. Decoherence, or decay, can be caused by the slightest disturbance in the qubit environment. This results in the collapse of computations or errors to them. A quantum computer must be protected from all external interference. Error correction during the computing stage hasn't been perfected. That makes computations potentially unreliable. Since qubits aren't digital bits of data, they can't benefit from conventional error correction solutions used by classical computers. Retrieving computational results can corrupt the data. Security and quantum cryptography is not yet fully developed. A lack of qubits prevents quantum computers from living up to their potential for impactful use. Quantum computers must have almost no atmospheric pressure, an ambient temperature close to absolute zero, and insulation from the Earth's magnetic field to prevent the atoms from moving, colliding with each other, or interacting with the environment. In addition, these systems only operate for very short intervals of time, so that the information becomes damaged and cannot be stored, making it even more difficult to recover the data. When a quantum computer is turned on to do an operation, a number of atoms are prepared to receive data after providing the necessary conditions for its stability. When a process starts, the quantum computer should be kept working without interruption or monitoring or any intervention of any kind until getting the final output to be translated at the end. The atomic structure and quantum process collapse every time an operation is accomplished. Quantum computing is based on billions of possibilities, and the delivered answers are also just calculated possibilities, which contrasts with traditional computers that give specific answers. The competition between many countries and corporations around the world in the field of quantum computing made them generously finance the research teams and institutions working on it, but still the achievements compared to the ultimate target are still insignificant. In a breakthrough by Google in 2019, they announced that they had passed a milestone known as quantum supremacy when their quantum computer Sycamore performed in 200 seconds an abstruse calculation they said would tie up a supercomputer for 10,000 years. Chinese scientists claimed that they have done the same computation in a few hours with ordinary processors. Also, IBM said that with certain arrangement of memories, order and structure can do the same task in 2.5 days instead of 10,000 years. Microsoft recently stated that its Azure Quantum program had achieved a historic milestone by proving the previously unattainable physics required to create scalable topological qubits. Azure Quantum program has developed devices that can create quantum properties which scientists have imagined for years but have not been able to unambiguously produce in the real world. It's a key scientific breakthrough that demonstrates the elusive building blocks for a topological quantum bit, or qubit, which Microsoft has long pursued as the most promising path to developing a scalable quantum computer that will launch a new generation of as yet unimagined computing capabilities. Finally, do you think that quantum computing research is progressing in the correct track? Do you believe that the creation of a viable quantum computer will soon achieve its goal, or if it will take some time?